Alright, so we're going to go through the 3 problems from quiz 6. A disclaimer real quick, or a little bit of a tip. When you're working through, especially quizzes or exams, every question has a title, and that title will give you a little bit of a hint as far as what you are supposed to be doing. So this first question says the function below has at least one rational zero. Use this fact to find all zeros of the function. And so we're given f of x equals 2x cubed minus 3x squared minus 32x minus 15. So it tells us that this function has at least one rational zero. So that should be a tip-off that we need to use the rational zeros theorem, which pretty much everybody did, but then you stopped there. It wants us to find all the zeros. So we're going to start with the rational zeros theorem that tells me to take the factors of p, which is my constant, and divide them by the factors of q, which is my leading coefficient. So all of the factors of p, factors of 15, we have 1, 3, 5, and 15. And the factors of q, my leading coefficient, 1 and 2. So the possible rational roots, these are the rational roots that I could possibly have. And another way of saying that is if this function has rational roots, it will come up in the list that I'm about to write. We're told it does have one, so we know that one of the numbers on the list I'm about to write is a solution. So possible zeros, possible rational zeros, how about PRZ? Each of the p's over each of the q's. So I'm going to take each one and put it over 1. I just get that value back. So I have plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. And then each of the p's over 2. So I have plus or minus 1 half, plus or minus 3 halves, plus or minus 5 halves, and plus or minus 15 halves. So this is my list of possible rational roots or possible rational zeros. Since I know this function has at least one rational zero, I know that at least one of these is a solution. To figure out if it's a solution or a zero, I can use what's called the factor theorem. And I believe that's in the title of this as well. So the factor theorem tells me if one of these numbers is a zero, then I can plug it in and it should equal 0. So that's what I'm going to do. I'm going to take f of, I'll start with positive 1. I'll plug in 1 and see what I get. When I plug in 1, this gives me 2 minus 3 minus 32 minus 15. I got 2 minus all of these numbers. There's no way that's going to give me 0. So 1, positive 1, is not a 0. So I'm going to go to negative 1. F of negative 1. That'll give me negative 2 minus 3 plus 32 minus 15. Negative 2 minus 3 is negative 5, minus 15 is negative 20, plus 32 is not 0, and I need it to be. So negative 1 isn't a 0 either. So I'll go to positive 3. Is 3 a 0? I'm gonna cheat and put this in my calculator. The numbers are getting big, man. So 3 cubed is 27, times 2 is 54, minus 27, minus 94, minus 15. So I have all these big negatives, and this one positive, that won't equal to 0 either. And so I'll keep going. I'll go to negative 3. And if that doesn't work, I'll go to positive 5. If that doesn't work, I'll go to negative 5, so on and so forth. If I can find just one, then I can use division to reduce my cubic down to a quadratic, and then I can use any method to solve for the remaining 2 zeros, right? This is a cubic, so I will have 3 total answers in this problem. So let me fast forward real quick and find the 0. Alright, so 3 isn't, let's check negative 3. So that's going to give me negative 54 minus 27 plus, oh, it was 96, my bad, plus 96 and minus 15. So let's see what that will equal. Negative 54 minus 27 plus 96 minus 15. Voila, it equals to 0. So I know that negative 3 is a 0. So negative 3 is a 0. And so if I wanted to write that back as a factor, this is x equals negative 3. So to write it as a factor, I just need it equal to 0, so I add 3 to both sides. X plus 3 is a factor. This problem specifically asks for the zeros, so I'm going to keep it as the zeros. If it wanted me to write this as a product of linear factors, then I'd want to work with the factors. But this one's the zeros, so I'm going to keep it with the zeros, which means I'm going to use synthetic division to break this problem down. I want zeros. You could use long division if you wanted to with the factor, but I'm going to use synthetic division. So I have my negative 3, the coefficients of my original function, bring them to 2, multiply, add, multiply, add, multiply, add. There we go. So this reduced my cubic down to a quadratic. So I have 2x squared minus 9x minus 5. So this is what I'm left with when I take x plus 3 out of my original polynomial. So now I've condensed it down or broken it down into a linear factor, which we know if I set that equal to 0, I get negative 3 as my 0, and a quadratic factor. So we can factor this. I can use the quadratic formula. If you're fancy and you want to use completing the square, that's totally fine. I just need to set it equal to 0 and solve. So this one does end up factoring. What does it factor into? I know I will have a 2x and a 1x. So I get 2x squared minus 10x plus 1x minus 5. There we go. And that gives us the 2x squared minus 9x minus 5. So I factored it. If you don't know how I came up with that, watch the AC method video to get a little more acquainted with that. So now I have it in factored form. I'll set each one equal to 0 and solve. So I get x is equal to negative 1/2. And x is equal to 5. So this problem, all of its zeros ended up being rational, aka pretty numbers. And we can go back up. We made the list of possible rational zeros, which again means if this function has rational zeros, they will appear in this list. And you can see negative 3, yep, right there, it's in the list. Negative 1/2, yep, right there, it's in the list. Positive 5, right there, it's in the list. So here are all the rational zeros of this function. Alright, so the next problem, kind of along the same lines. We're still working with a polynomial and we're talking about its zeros. So this one says, suppose that r of x is a polynomial of degree 9. What does that tell me? This polynomial will have 9 zeros. Be it real, be it non-real, positive, negative, it's going to have 9 of them. So whose coefficients are real numbers? Also suppose that r of x has the following zeros. So we know r of x has 5i and negative 5 plus 4i as zeros. So the first part of this question says find another zero of r of x. Well, by the complex conjugate theorem, we know if I have a non-real solution that they come in pairs. So part A has 2 possible answers that you could use. 5i is non-real, so negative 5i is also a solution. And negative 5 plus 4i is also non-real, so it has a counterpart. The way you find it, the conjugate, you do the opposite of the imaginary part. So you could have done negative 5 minus 4i. So these are 2 other zeros that we know r of x has. So pause real quick. We know 1, 2, 3, 4. 4 right off the bat. 4 of them are non-real. So that leaves 5 that we don't know anything about. So part B says, what is the maximum number of real zeros R of x can have? Well, I know 4 of them are non-real, and the rest could possibly be real. So part C, I'm going to skip that for just a second. Part C says, what is the maximum number of non-real zeros that R of x can have? The thing to remember is what we just talked about up here. The non-real values, zeros, come in pairs. So what that tells us is the maximum number of non-real zeros always has to be positive. This polynomial has a degree of 9, but I can't have 9 non-real solutions. I can only have an even number. So it would have to be 1 less than that. We don't know that it has any real at this point. I only know it has 4 non-real. So this could have up to 8 non-real zeros, right? Because I'm not restricted. It doesn't tell me that there are any real. If there was like a 3 out here or something, that might change things. But it doesn't tell me that there are any real, so this could have up to 8 non-real zeros. Now going up to part B, what's the maximum number of real zeros R of x can have? Real zeros don't have a constraint as far as if they come in pairs or not, right? A cubic, we just saw in the first problem, could have 3 real solutions. So they don't have to come in pairs, so we can have an odd number of real zeros. We know that this thing already has 4 non-real. That leaves 5 possible real zeros left. Zeros left. So there we go. Alright, so the last problem asks us to graph the rational function. So this again, a lot of people emailed me wanting to know why their graph was wrong or was counted wrong. A clue can be found in the title of this. It's graphing, It's graphing rational functions with holes. That is the name of the question. So that should be a dead giveaway. This problem has a hole and you need to graph it. So with rational functions, if you're graphing, the very first thing right off the bat is to write this in factored form. So I see I can pull a 2 out of the top. That leaves me with 2 times x minus 4. And the denominator, it's a pretty little quadratic that does factor. This factors into x minus 4 and x minus 2. I see the x minus 4 is common in the numerator and denominator, which means that I can cancel it out and this is going to create a hole. So I know I have a hole at the coordinate, right? This is a point. So if x equals, or x minus 4 equals 0, then x is equal to 4. So the x value of this is 4. I need to find the y value. So to do that, I'm going to use what we call the reduced or the simplified form, which is just what I have left when I cancel out that common factor. So I now am working with 2 over x minus 2. And if I want to know the actual coordinate of that hole, I'll just plug 4 back into this. So if I plug in 4, I get 2 over 4 minus 2, which is 2 over 2, which is 1. So I know I have a hole at 4, 1. So I need to plot that on my graph. You will absolutely see this again, possibly on the upcoming quiz. Give you a little chance for redemption, but definitely on the final exam. So there's the hole. I also need to find x-intercept, y-intercept, and my asymptotes. So let's start with the asymptotes real quick. Again, for the rest of this problem, I'm just going to work with my simplified or reduced version of this problem. The horizontal asymptote, remember there's 3 cases that we could have. We have the case here where the degree of the numerator is less than the degree of the denominator, which indicates that I will have a horizontal asymptote at y equals 0. My vertical asymptote, shorthand this. Vertical asymptotes come from where the function is undefined minus the hole. So I'm just looking at where x minus 2 is equal to 0. So in that case, I get x equals 2, and there's my vertical asymptote. To find any x-intercepts, I take that reduced function and set it equal to 0 and solve. So here we go, solving a rational equation. How do I solve a rational equation? I multiply by the common denominator. Only denominator I have is x minus 2, so I multiply both sides by x minus 2. On the left, the x minus 2's cancel out, leaving me with 2. On the right, 0 times x minus 2 is 0. There's no value in the world that makes 2 equal to 0. So what that tells me is this equation has no solution. What we were trying to find was an x-intercept, so I don't have any. This will not touch the x-intercept, or the x-axis. Alright, y-intercept. To find the y-intercept, I plug in 0 for x. So I have 2 over 0 minus 2, which is 2 over negative 2, which is negative 1. So I have a y-intercept at the coordinate 0, negative 1. And there we go, I found all the pieces. I have a y-intercept at 0, negative 1. I don't have any x-intercepts. I have a vertical asymptote at x equals 2, horizontal asymptote at y equals 0, and a hole at 4, 1. So this should be enough to know what that graph looks like. If not, we can do a little extra plug and chug to see what this graph should look like. But let's put our information down and see what we got. So I have a vertical asymptote at x equals 2. So here's 2. I know I have this right here. My horizontal asymptote is at y equals 0, so that is the x-axis. So it makes sense that we don't have any x-intercepts. My y-intercept is at 0, negative 1. The y-intercept is right here. I have a hole at 4, 1. So here's 3, 4, positive 1. A hole right there. This only has one vertical asymptote, so I know it splits my graph into 2 pieces. I have a hole in the top right. I have a point in the bottom left, so I know exactly where the line should be. I'll have one in the top right, so goes through that hole. And I'll have one in the bottom left. So skating close to my asymptotes. There we go. There is the graph of that rational function.